Hello, guess what? It's time for more stoichiometry. Always, it never ends, I promise. When we're dealing with solutions, if you think about what we did before with these meta-ionic equations, we have a chemical equation. It's got solids. It's got solutions. So we can do stoichiometry. We can convert between different chemical species. So let's kind of crack right into a problem here. So we have the situation, we've got lead nitrate it's the same, we're actually going to use the same formula as the same equation as before. So we're going to use this equation. So we've got the potassium phosphate is reacting with lead nitrate to form potassium nitrate and lead phosphate. So how many milliliters of a 2.5 molar lead nitrate solution, liters, that's what we're solving for, and here's our solution, are needed to make 14.2 grams of lead phosphate, as long as we have excess amount of potassium phosphate. So this is a stoichiometry problem. Now, if we were looking at this from a purely, like from our kind of initial forays into stoichiometry, this looks like we have a good starting point. We've got this grams of lead phosphate. That's how much we're trying to make. So we have grams of lead phosphate, and we're trying to figure out something about lead nitrate. I mentioned this sort of before, but when we're talking about molarity, you can kind of think of molarity, it's similar to molar mass in a lot of ways. Okay, so molar mass relates grams to moles. Molarity relates moles to milliliters, or moles to liters, or moles to volume. So in a way, what we're trying to do here is we need to figure out how many moles of lead phosphate we're trying to make, how many moles of lead nitrate it's going to take to make that amount. And then we can use this molarity to convert it to milliliters or liters. So let's just kind of dive right in and give this one a try. This particular problem, I think we can solve in one skeleton. So we've got our starting point, the lead phosphate, and we got our equation up here. So we're going to start with the 14.2 grams of lead phosphate. And we need to convert this into moles. So we're going to need to do molar mass. And I did not calculate this ahead of time, which I probably should have, but it's okay. We'll do it together. Okay, so lead phosphate is going to be 3 leads. Lead is very heavy. It's 207.2. Whoops. If I can type this, 207.2 times 3. And we're also going to need to add on, how many was that? That's going to be 2 phosphoruses. So that's going to be 30.97 times 2. And we're also going to need 8 oxygen. So 16, let's do plus 16 times 8. Whoop, I made a mistake. Second answer, plus 16 times 8. Hopefully this will work. Yeah, it seems reasonable to me. 811. Put your lights back on. It's going to be a pretty big number just because that lead, I mean, the lead alone is like 600. Phosphorus is no lightweight either. So 811.54 grams of lead phosphate per 1 mole of lead phosphate. Okay, so far we've converted from grams to moles. We now know how many moles of lead phosphate we are trying to get. It's going to be a pretty small number because 14 divided by 800 or 15 divided by 800, something like that is not going to be very big. Okay, the next step is cross that out. Here, I'll use a red pen. Why not? That could be fun. Get a color in there. Now we've got moles of lead phosphate. We need to see what's the connection between lead phosphate and lead nitrate, so a molar ratio. So it looks like for every 1 mole of lead phosphate, based on our balanced chemical equation, it takes 3 moles of lead nitrate. So now we have moles of lead nitrate. Now, normally in this problem, maybe we'd stop here. We'd say, okay, we just want to find moles of lead nitrate. How many moles of lead nitrate it takes to get 14.2 grams of lead phosphate. Or we might want grams, so we'd use molar mass. But in this case, we don't want grams, we don't want moles, we want milliliters. So we are going to use the 2.5 molar as our equality. So what this is telling us is that 2.5 moles of lead nitrate is dissolved in 1 liter of the lead nitrate solution. So I actually need to reverse that. I did that wrong. This is why this is good. Okay, 2.5 moles. This is why I like to do skeletons, because it makes me check my work. Okay, so that's going to give us liters of lead nitrate, and I'm kind of running out of space, so we're just going to stop there for right now, and then we'll do the milliliter. You could actually normally put the milliliter in as well. So it looks like we're going to need to do 14.2 divided by that molar mass, which is for me a second answer, times 3 divided by 2.5. And that's going to be 0.021 liters, which in milliliters is going to be 21 milliliters. And that's our final answer. Okay. So the process, again, pretty much the same as any old stoichiometry problem. It's just figuring out where you need to start and where you need to end and how to convert. Oh, that bell, so exciting. Okay, so let's go through, I think more examples will help. I think that's the best thing for this. So let's go check out a couple more examples. You have 2 pages in your packet that relate to this. There's page 17 and page 18. So let's do that. Put these notes aside for just a moment, get them out of my face. I don't need them. You know the information now. Periodic table that we'll probably need. All right, I'm going to do number 2 first, and then I'm going to do number 1, and then I want to talk about why that is, and we'll get it all set up. Okay, so how many milliliters? Oh, same kind of problem. Of a 0.28 molar barium nitrate solution are required to precipitate as barium sulfate all the sulfate ions. So we're trying to precipitate all the barium sulfate ion out from 25 milliliters of a 0.35 molar aluminum sulfate solution. Okay, so we have aluminum sulfate. We've got 25 milliliters of it. It's a 3.50 molar solution. And we're going to use barium nitrate to precipitate out all, to get us all, like to get rid of, to basically fully react, to fully precipitate out all the sulfate ions. So it looks to me like we are going from here to here. Okay. We have information about the aluminum sulfate. We know how many milliliters we have, and we know how many moles, the molarity or the concentration of it. So what we really need to do is figure out how many moles of aluminum sulfate are there, how many moles of barium nitrate it's going to take to fully react with all those. So that's the molar ratio part. And then convert that number of moles and figure out how many milliliters of this solution we're going to need. So let's set up the equality. And by that, I mean skeleton with equalities. So my starting value is actually going to be this 25 milliliters. And I'm just going to go ahead and convert that into liters. You can totally do that within the skeleton. There's no problem with that. But I just did it really quickly because it's easier. And we've got our molar, I got our molarity here. This is milliliters and liters, I should write this, of aluminum sulfate. So that's going to be for every, we need 1 liter on bottom, we need 0.350 moles of aluminum sulfate. And again, I like to write everything out, even though I know it's insane, because I make so many mistakes. And if I don't do all of this, if I do all this, I correct my own mistakes, like you just saw. It's so easy to make mistakes. And even with this system, I still make them sometimes, but this way we can at least reduce the frequency of those mistakes. So that cancels out. So we're at moles. This is a balanced chemical equation. So it looks like for every 1 mole of aluminum sulfate that reacts, it's going to take 3 moles of barium nitrate. So our moles of aluminum sulfate have been canceled out. And now we just need to convert moles of barium nitrate into milliliters or liters of solution. So I'm going to actually not make the same mistake again. This number here is moles, is 2.8 moles for every 1 liter. So that's 0.280 moles of barium nitrate for every 1 liter of barium nitrate. And because I've got a little extra space, I'll throw this in here. There's 1,000 milliliters in 1 liter. So, oops, excuse me, our moles are going to cancel here. Our liters will cancel, and we'll just be left with milliliters as our only unit. And that's exactly what this problem is looking for. So let's just do the math. So the math is going to be 0.025 times 0.35 times 3 divided by 0.28 times 1,000. And we get 93.75 milliliters as our answer. And does that make sense? Yeah, I think so, because the concentration of the barium nitrate was lower than the aluminum sulfate. So we, even if it were a 1-to-1 ratio, we would need a little bit more than 25. But being that we need 3 times as many moles of barium nitrate, we're going to need 3 times as many milliliters. So we're looking at least 75 milliliters. And 93 makes perfect sense because we need a little extra. Okay, so that's that kind of problem. Cool. Okay, let's try one that's a little bit tougher. Let's see what's happening with this one. And by tougher, I mean more complicated. It's not more difficult. It's just there's lots of steps. Chemistry is all about simple versus complicated. The simple things are like, what's the, how many moles are is in this many liter of this, molar solution? That's pretty simple, relatively. These kinds of problems, just adding more steps. Each step is not that hard. There's just a whole bunch of them, and knowing which order to do it in can be a little complicated. Okay, so how many grams of silver chromate, that's our answer that we're looking for, will precipitate when 150 milliliters of 5 molar silver nitrate are added to 100 milliliters of 4 molar potassium chromate? Oh man, guess what this is? This is a limiting and excess reactant problem. Okay, so I've marked these off on the actual on here. I didn't put it in your packet itself, but on the answer key, you'll see number 1 and number 3 on this page. And if you go to the next page, number 8, these are all limiting and excess reactant problems. So the first thing we have to figure out is we know that we've got silver nitrate and potassium chromate are both reacting, and they're going to form this silver chromate. We have to figure out which one is the limiting and which one is the excess reactant. So I think what I'm going to do is I think I'm going to do these problems, and I'm not going to convert all the way to grams of potassium chromate. I think I'm just going to convert to moles of potassium chromate to figure out which one's the excess and which one's the limiting, and whichever one is the limiting, that's the one I'll convert to grams. So I'm going to start with volume and molarity of both of these and convert to moles of silver chromate, and we'll see where that leads us. We're going to need 2 skeletons, one for the silver nitrate and one for the potassium chromate. So let's see how we can squeeze that all in here. I think we'll manage. So let's do the silver nitrate first. So we're going to be starting off with 0.150 liters of the silver nitrate. And the molarity is 0.500 moles per 1 liter of silver nitrate. Okay. And now we need to convert that into silver chromate. So it's going to take 2 moles of silver nitrate to make 1 mole of silver chromate. Okay. So that's our first skeleton. Liters cancel, moles cancel. We're left with just moles of silver chromate. Gosh, how do I want to do this? Okay, I'm going to try to squeeze in the other skeleton right underneath. I don't know why I'm sweeping it off. There's no like eraser dust, but there you go. Okay, same thing up here, similar, but we're going to do it for potassium chromate this time. The potassium chromate, we have 0.100 liters. That's that milliliters of potassium CrO4. Yeah. The concentration is 0.400 moles of potassium chromate for every 1 liter of potassium chromate. And then this is a 1-to-1 molar ratio. So 1 mole of potassium chromate for every 1 mole of silver chromate. We got that from the molar ratios right there. Once again, all of this is going to cancel. Liters, liters, moles, moles, and we'll bam. I suspect that they're going to be pretty close. Okay, so we've got 0.15, I'm doing the top one here, times 0.5 divided by 2. It's going to be equal to 0.037. 375, pardon me. So that's going to be moles of silver chromate. And then the other one is 0.1 times 0.4, and that's pretty much it. 0.04. Excuse me, moles of silver chromate. Ooh, man, this is really close. There's barely a difference. However, silver nitrate is definitely the limiting. And chromate, potassium chromate is the excess. So we're going to use this one. We're not going to worry about it. So we're going to need to convert this one. I'm not going to worry about that one. Let's convert that to grams, that number into grams. So we need to know the molar mass. 1 mole of silver chromate. What is the molar mass of that? I don't know. Let's look it up. Okay, silver is 107.87 times 2 equals plus the chromium's here is 52, plus it's going to be the 4 oxygens, which is 64. Just kind of know that off the top of my head because it's 16 times 2 is 32, and then 32 times 2 is 64, blah, blah, blah. There you go. Okay, so 331.74 grams, and that's going to lead us to our answer. Let's just multiply that times 0.0375, and that's going to be 12.44 grams of silver chromate. That's our answer. Okay. Whew. A lot of work, a lot of calculations, but you know, that's what you got to do. So again, limiting and excess reactants make this a little bit more complicated. Okay, there's more here for you to practice. There's another limiting and excess. This one is much more straightforward. Some of these involve mass, some of them don't involve mass at all. So you'll notice in this problem, we had to use molar mass, but we also use molarity. You can kind of mix and match. It's just whatever the problem requires. Again, the most important part here, this is the key, that molar ratio, man. The molar ratio is the most important part of this problem. Everything else is just kind of getting to moles, whatever it takes to get to moles. We can throw in a gas if we wanted to with this. Maybe you have a gas interacting that's reacting with, ooh, this is fun. If you have a solid that's interacting with a solution to produce a gas, you could end up using all 3. It's crazy and it's awesome. And I'll probably make you do it at some point, especially in AP Chem. The last page is page 18. There's another limiting and excess reactant problem there. I'm just gonna turn this on. And this one's a little funky. You have to remember about the hydrates and how the hydrates are going to interact, might affect your molar mass in a particular way. So that one's a little funky. If you get stumped by that one, that's reasonable. Maybe I'll do the answer for that one eventually. These two should both be fairly straightforward as far as stoichiometry goes. All right, enjoy. It's going to be great. This is insanely important for AP chemistry. This is the kind of thing that you definitely want to be able to do. If you're not planning on taking AP chemistry, not as big a deal. So there you go. Enjoy, everyone.